Hello, everyone. My name is Patrycja Węgrzynowicz, and today I'm going to tell you about the security, or rather insecurity, of JSON Web Tokens. First, a short introduction. I've been doing professional software development for over 20 years. My interests focus on patterns and anti-patterns in software. I work on tools for automatic detection and refactoring of software defects, such as performance anti-patterns, database issues, and last but not least, security vulnerabilities. So basically, security is my daily job, or rather one of my daily jobs. What am I gonna talk about today? First, a brief introduction to JSON Web Tokens, just for all of us to be on the same page. The key part of today's talk involves 4 demos that reveal some security problems with the spec, the implementation of tokens libraries, and some problems with our applications. There are a number of caveats which concern JSON Web Tokens. And we'll start with the first difficult thing, which is, how do we actually pronounce it? And it turns out it's not a piece of cake. As a native Polish speaker, I pronounce it as JWT. In English, I usually hear the pronunciation as JWT, but the RFC suggests the same pronunciation as the English word JWT. By the way, JWT in English means a brief informal note, just as JSON Web Tokens are short, less formal tokens. However, in today's talk, I will pronounce it as JWT. Why? Because simply it's the most popular version in the software world. Plus, I'm not sure whether I pronounce JWT clearly enough. So JSON Web Token is a set of claims that encode users' identity and usually users' permissions. It also consists of a digital signature to protect its content against tampering. It's always handy to take a look at some sort of an example. We see that a JSON Web Token is a long string consisting mostly of letters and numbers. We can recognize 3 parts separated by dots. These 3 parts are a header, payload, and a signature. All 3 base 64 URL encoded. When we decode these 3 parts, we see that the header and the payload are just JSON strings. The header contains an algorithm used to generate a signature. In our example, it's HS256, HMAC with SHA-256. The payload contains the actual claims of the token. In our example, it contains 4 claims: subject, issued at, issuer, and expiration. The signature is just a binary content. Here we also see the very first problem of JWT, the lack of confidentiality. The tokens are not encrypted. They are only encoded. So it's easy to decode them and see all data available in claims. Therefore, we should avoid enclosing any confidential information in those claims. JSON Web Token is generated on the server side, then it's stored on the client side, usually in the session storage. Then with each subsequent HTTP request, the token is transmitted to the server, usually as part of the authorization header. Then on the server side, the token is verified. And in case of an incorrect token, the request is rejected. It sounds very simple. So now it's time for the reality check. Let's take a look at some security problems of JSON Web Tokens. Before the first demo, some organizational information. I will need your cooperation during demos. I would like to show a live hijacking of your accounts. So my kind request to you, please go to the demo application. The link is available at my Twitter account, Yon Labs. And also you can see it on the screen. Please register your account and log in. You can see my Twitter account. There is a tweet with a link included. Please go to the demo application, log in, register first, log in. Obviously, do not use any real data, real passwords. Those accounts are supposed to be hacked. So now it's time for the first demo. The first demo reveals a problem with the none algorithm. In JWT spec, there are only 2 mandatory algorithms to be supported by library. The first one is HS256, and the second one is none. None basically means no algorithm, no signature. In my demo, I will show you how to use the non-algorithm to bypass server verification. Okay, so I'm refreshing. Oh my God, there are so many new accounts. Thank you for your cooperation. Okay, so you see that there is a token, JWT token. When we copy it and see the details, we see that this is an HS256 token. There are some claims. Subject is 1. I have a fake token available. The token I have prepared, it has non-algorithm configured. Basically, there is no signature. And it's configured to represent a user with ID 3. So I'm just copying this token. And hijacking is very easy. Going back to my application and replacing the token, refreshing the page, and congratulations, Nick, your account has been hijacked. So basically, why was such a token accepted by the server? The problem here is in the code, obviously. We have a vulnerability in our verification code. And unfortunately, it's a mistake one can make very easily. What's the mistake? At first sight, our verifying method looks fine. However, it's not. We've used the parse method, which only decodes the token and does not verify signature. So instead of parse, we should use parse claims JWS. I must admit that the naming in this library, IO JSON Web Token, is not very intuitive. And it's not the only library with the none problem. when we search the national vulnerability database, we can find many, many more issues related to JSON Web Tokens. One of those issues reveals the non-problem in another library, albeit much less popular. Check out the year of the entry. The issue was raised in 2018, so only 3 years ago. How many applications are not patched yet? Who knows? There are 3 main problems revealed by our first demo. The first problem is the presence of the none algorithm in the RFC. I guess that the intent was to use the none algorithm in a controlled environment like internal network. However, even in such cases, I wouldn't say it's recommended, or rather I would say it's not recommended from the cybersecurity point of view. The second problem is the misleading APIs in JWT libraries. And the last but not least problem is with us, developers. We often don't read manuals, we use samples found in the internet, so such mistakes happen. And actually, the exact mistake I showcased you happened to one of my projects. So to protect our code against such problems, we should understand the library in use. Check out vulnerability databases. And additionally, in our code, we should require a specific algorithm and a specific key during verification. Why should we require a specific algorithm and key during verification? Because otherwise, we can end up with serious vulnerabilities in our code, like this one. When a hacker can trick a vulnerable application to change the algorithm to HMAC SHA instead of RSA. Let's take a look at the attack scenario. For a regular user, the server generates a token signed with a server RSA private key, and the server verifies sent token with a server RSA public key. For a hacker, the hacker generates a token signed with a server RSA public key used as an HMAC secret. The server verifies the token using an algorithm set by a hacker, and the server uses its public RSA key for verification. So that's how the attack can happen. And here is another reason why to require a specific algorithm and a specific key. It's another vulnerability where a hacker can provide his own public key for the server to verify a token. Actually, the library followed the standard, and that was the root cause of the vulnerability. The standard specifies that a JSON web key representing a public key can be embedded within the header. That's another problem with the standard. The main paradigm of cybersecurity: never trust the client. Let's take a look at this scenario. Basically, for a regular user, the token is signed with a server RSA private key and verified with a server's RSA public key. For a hacker provides his own RSA signs a token with his own RSA private key and provides RSA public key in JWT header. So the server receives the public key for the verification, uses this public key for verification, and the attack is successful. Here's something more optimistic. The library with quite nice API design supporting security. Please note how strong typing and object-oriented programming help to achieve good security. We have an abstract algorithm with several subclasses. A key and an algorithm are packed together, so no problem with a different interpretation of a key, like in that example of RSA key used in HMAC context. And as developers, we quite often see programming to primitives, like usage of integer or strings instead of classes. It usually leads to a lot of if-then else statement and quite messy code. And with messy code, messy code basically is a primary source of security vulnerabilities. So my advice, use a good library. Let's move to the second demo. The second demo is a demonstration of a key cracking of HS256. HS256 stands for HMAC with SHA-256, hash-based message authentication with SHA. The algorithm requires a secret key. It's a symmetric algorithm, which means the same secret key is used for generation and verification of a signature. As this is a symmetric algorithm, once we get to know a secret key, we can generate our own tokens to be accepted by the server, and we can impersonate another user. For password cracking, I will use hashcat. Hashcat is a free and open source password cracker. Sorry, I'm very, very sorry. It's not password cracker. They call themselves a password recovery tool. First, we need to grab a real token. So again, I will log in to our application. I will copy the token for hashcat to crack it. For password cracking, I will use a GPU-powered machine. Hashcat is optimized for GPUs, so for parallel processing and GPUs, so it will be much, much, much faster than on my local laptop. I will log into my GPU-powered server. I will show you hashcat configuration, hashcat information. Basically, it's hashcat 5. For efficient cracking, it's better to use hashcat 6 because it has support for CUDA library. Hashcat 5 only supports OpenCL, which is like about 30% slower than CUDA. But it was easier to configure for me. Basically, we have two GPUs. It's GeForce RTX 2008 Ti. It has like over 2,000 cores, but only 2 GPU cards. Okay, basically I have a short script configured for JWT cracking. It's just simple brute force for hashcat and the specification of cracking JWT algorithm. And we'll see how it goes on. Basically, first we see initialization of GPUs, OpenCL, etc. And here the cracking starts with, okay, it's done. It was really very fast. Basically, it took like 20 seconds, 15, 20 seconds to crack the password, the secret of HS256 algorithm. It's 4Dev May 21. And now when we know the secret, we can generate a new token. So basically, let's choose the subject 7. We have secret configured, and this is our new token. I'm copying the token, and again, replacing the token in the session storage, refreshing the page, and now I'm logged in as QWERTY123. Congratulations, you've been hacked. Basically, hashcat is one of the most popular password recovery tool. It runs very, very fast and supports more sophisticated ways of cracking, and it supports many different algorithms. You can see the comparison of efficiency of password cracking on my local laptop. It's about 5 million hashes per second to GPU-powered machine, which is like 2 billion hashes per second. So much faster. So the obvious problem revealed by our second demo is weakness of our secret key. Another problem is that for the key cracking, the hacker needs only one token, and all cracking is done offline without any communication to the verification server. Therefore, there is no method to detect such brute force attacks, and a victim remains unaware of the attack. And once a hacker knows the secret, he can generate whatever token he desires, impersonating any user. It turns out it's pretty complicated to adjust our keys and algorithms properly, as there are many algorithms and different kinds of keys possible. There are 4 main algorithmic families available for JSON Web Tokens. The first 2 are the most popular, HMAC with SHA and RSA with SHA. As it comes to HMAC with SHA, the recommended key length is as long as the length of the hash. So for HS256, at least 32 bytes. It's worthwhile noting that it's a symmetric algorithm. So the shared key is used for generation as well as for verification of the tokens. Therefore, the secret key must be present on each server. So when one server is compromised, the entire system is compromised. In case of RSA with SHA, and the recommended key length is 2K bits at minimum, RSA is a asymmetric algorithm. So it uses separate public and private keys. And in case of a scalable environment, farm of servers, only authentication servers possess the private keys, and verification servers use only public keys. So therefore, the attack surface is decreased in such a case. In third demo, we will switch to HTTP because I want to steal one of your tokens by packet sniffing. Okay, I will log in to my main server. I will run TCP dump, and I will post a link to HTTP for you. So please use HTTP-based version now. Oops. Okay, posting the link. Obviously, when we use HTTP, I could capture your passwords as well, but in my simple TCP dump script, I'm grabbing for bearer, which is basically associated with authorization header. Okay, so there are some tokens coming in. Thank you. I will copy one of those tokens. Again, I will log in only as Patrycja. And again, I will go to session storage and replace the token and refresh the page. Oops, that's Nick again. I will try another token. Just to hijack another user. Oops. This should be different. This one should be different. Okay. We have another user. Thank you for your cooperation. We managed it. Okay. So as you can see, the problem is that the stolen tokens, the obvious problem is lack of encryption. Another problem is that the stolen tokens can be freely used as long as they are valid. Oops, sorry. So the main problem was the lack of encryption. So let's move back to encrypted communication channel and let's use HTTPS and let's see whether or not we can steal one of your tokens. I think I still be able to hijack your sessions, this time by exploiting an XSS vulnerability to steal one of your valid tokens. Okay, so let's move to application. I have a simple XSS attack prepared. Basically, it's a simple JavaScript because, as you can see, we have a simple form available. And as you can expect, this simple form has an XSS vulnerability. So basically, I will update my profile. You can see there is now a link under my name. And now my kind request for you to click those links. And I will go to my evil server this time, where your JWT tokens are sent to during this attack. Okay, so logging into another server. Basically, the evil server just is a simple web server that just stores whatever parameters are sent to it in logs. So I will observe logs. Oh, and I see new tokens coming in. So now to be quick enough to capture one of those tokens. Thank you for such a nice cooperation. And again, replacing this token, replacing my token with this stolen one. Okay, now I'm logged in as Confidentiality. Thank you. So even with HTTPS, I managed to steal one of your tokens. The only tricky part of the malicious JavaScript is that we do not connect the evil server directly. We connect via loading the link as an image source. This way, we bypass the same origin policy implemented in browsers. So, what are the problems and what are the solutions? Obviously, we have an XSS vulnerability in our application, so we should apply the best anti-XSS practices, because there is no other way to block access to a session storage for JavaScript. So best practices for anti-XSS is to use content security policy, to make use of some code audits, pen testing to discover XSS, good libraries and smart usage, obviously. But also, instead of session storage, we could use hardened cookies as a storage mechanism for JWT. Hardened cookies with such flags as secure, HTTP only, and same site. But in case of hardened cookies, we have another problem because we need to protect against CSRF, cross-site request forgery. Also, to protect against token sidejacking, there is another solution recommended by OWASP. OWASP stands for Open Web Application Security Project. And basically, OWASP recommends a solution based on a random secure value sent in a token, as well as in a hardened cookie. If you want to know more, please read the explanation in the OWASP cheat sheet, because we don't have so much time to deep dive into this approach. But basically, the verification servers verifies whether a cookie value and JWT fingerprint values are equal. We send token in authorization header as well as random secure value in a hardened cookie. And what you've seen today, it's only the tip of the iceberg when it comes to JWT security. In addition to algorithms, implementation, protecting against eavesdropping, XSS, etc., we should consider logouts and timeouts as sort of a basic hygiene for, say, secure applications. Unfortunately, JWT does not provide any built-in feature to revoke a token or expire a token after inactivity period. So again, it's up to us, developers, to implement those things correctly. And so again, even though JSON Web Tokens are self-contained and stateless, the state strikes back. We need to keep some sort of storage to keep, for example, invalidated tokens. And one more piece of advice, remember, a fool with a tool is only a fool. We, developers, can't be fools. We need to know how to use our tools wisely. And in software development, we have continuous integration, we have continuous delivery. I always talk about continuous refactoring, but the fundamental paradigm is continuous learning. So as developers, we must keep learning. That's all for today. Thank you. Now it's time for your questions. I oddaję głos do studnia.